Now, in fact, Gibbons rotations, though used by Gibbons, were not invented by Gibbons. They're actually invented by Jacobi. We use them for a very different purpose than what we're going to deal with. Okay. So, now, the idea behind a Gibbons rotation is this. So given, pun not intended, I swear, you have a vector x that has these two elements, a1, a2. So you want to find an orthogonal 2 by 2 matrix. G that has this form, C minus S, S, C, such that G transpose times X has the effect of zeroing the second element. And then the first element will be some number R. Now, R is going to be the square root of the original element squared. Also, in order for G to be an orthogonal matrix, we need G transpose G to be identity. So in fact, we have C squared plus S squared is equal to 1. And then in fact, what it means is C and S form a cosine sine pair. So C is equal to cosine theta for some theta, and S is equal to sine theta for that same theta. So it's another approach to zeroing elements. So in that sense, it's kind of like, in spirit, it's like Gaussian elimination. The difference is we're trying to compute the QR factorization with Q's an orthogonal matrix. So we need to use orthogonal matrices to perform elimination of this element here. So that's why we have this structure. Okay, so now what we're going to do is use this equation to figure out what C and S need to be. So from G transpose X is equal to R0, if I write out what that is entry by entry, so I have CS minus SC, A1, A2 is equal to R0, so I get CA1 plus SA2 is equal to R, and then minus SA1 plus CA2 is equal to 0. So what I can do from the second equation is, there's actually two solutions. But, so for instance, I could choose A1 to be equal to, well, first I'll choose them to be C, and A2 to be S, because then I have minus SC plus CS, which is going to be 0. But, no. Well, okay. These equations are not wrong. They're, this format is the wrong one. They're not my, A1 and A2 are not my unknowns. C and S are my unknowns. So C would be A1, and S would be A2. But I need C and S to be a cosine sine pair. If I just define it to be A1 and A2, I'm not going to have cosine squared plus sine squared equal to 1. So I'm going to divide these by 2 squared. And I'm assuming that x is a non-zero vector, or there wouldn't be any point to this. Okay. Right, so, yeah. So now I have my cosine sine pair, and sure enough, R is going to turn out to be, from this choice of C and S, I'll get, after simplifying, square root of A1 squared plus A2 squared. All right. So the matrix G with this C and S chosen in this manner is called a Gibbons rotation. Or, depending on the context, the Jacobi rotation. All right. So what I can do is I can use this to operate on any two elements of a vector in order to have the effect of zeroing one of them. So, for example, so suppose my vector x has this form, where I have some entries alpha and beta anywhere in the vector, and various entries in between that I don't care about. Okay. So alpha is in position I, and beta is in position J. So what I can do is I can let C be equal to alpha over square root of alpha squared plus beta squared. S be equal to beta over square root of alpha squared plus beta squared. And then my Gibbons rotation will have this form. So whatever the length of this vector is, and it's an n vector, this is going to be an n by n matrix. So in rows and columns I and j, I'll put my cosine sine pair. So I have C minus S, S, C. And then everywhere else in the matrix, I'm going to have identity of ones down the diagonal everywhere else, and then zeros throughout the rest of the matrix. So only rows and columns I and j are different from identity here. So then what happens is G transpose X is going to be, well, first of all the other entries of this vector are going to be unaffected. But alpha becomes the entry row, and then beta becomes 0. And everything else is undisturbed. And then the number row that's in position I, rho is equal to the square root of alpha squared plus beta squared. The reason for that is this is an orthogonal transformation. It preserves the 2 norm of the vector that it's multiplying. So the sum of squares of these elements is going to stay the same. All right, so that's a Gibbons rotation. So this is good for precision zeroing. We just want to go after a certain element, track it down, and get rid of it. Wherever it may be in the matrix, Gibbons rotation is the one to do the job. But like Gaussian elimination, it relies on some other non-zero element to help perform the elimination. Actually, nice thing about Gibbons rotations, this element, or really this element, doesn't have to be non-zero. So this is what we want to get rid of. It doesn't matter what this element is. If it turns out that this is 0, Gibbons rotation just amounts to a swap. Okay. Now, the last Gibbons rotation, and then we'll be out of time, is how to compute one with numerical stability. Because as you recall, in homework 1, computing something like the square root of alpha squared plus beta squared is susceptible to overflow. So in order to compute your cosine and sine pair with numerical stability, for the unexpected floating point issues, what you can do instead is the following. And I have some code posted on the site. Gibbons.m on the lectures page. And this is something that you'll be using in the final assignment. So I use this in the implementation. Let's suppose that beta is the larger of the two entries in your vector. So beta is actually the element you want to make 0. So what you can do is you compute tau is alpha over beta. So this is going to be a number that's guaranteed to be less than 1 in absolute value. And then your sine and your cosine sine pair plus the square root of 1 plus tau squared. And then your cosine is just your sine times tau. So that's a more robust way to compute your cosine sine pair. Otherwise, in a case where alpha is the larger, you just go the other way. So tau is beta over alpha, so now that's going to be still less than 1 in absolute value. Your cosine is 1 over square root of 1 plus tau squared, and then your sine is your cosine times tau. So it works in much the same way. Okay. Let's see. Yeah, I'm going to stop here. So on Wednesday, I'll show how you use Gibbons rotations to compute your factorization, and then get into household reflections and how you can use them instead.